We thought we could imagine the scale of the universe. In 2004, the Hubble Ultra Deep Field astonished us, revealing 10,000 galaxies and forming estimates that their number in the cosmos reaches 2 trillion. But everything we learned from this research was limited. Just a tiny point of invisible light that could not reveal what was hidden behind dust and redshift. Now, the James Webb Space Telescope has shattered these boundaries. During a campaign lasting 250 hours, the James Webb Space Telescope mosaic revealed almost 780,000 galaxies in an area no larger than 3 full moons, stretching back 13.5 billion years. The scale has not only increased, but the rules themselves have changed. How could such a level of structure and maturity arise from what once seemed empty? This is how the James Webb Telescope redefined just how vast the universe truly is. In 2004, astronomers pointed Hubble's gaze at what seemed to be an empty patch of sky and left it observing for over 11 days. The result, known as the Hubble Ultra Deep Field, became an icon of modern astronomy. What seemed like emptiness turned out to be home to nearly 10,000 galaxies, each a vast island of stars, some shining at us from over 13 billion light-years away. This single image, just a dot against the night, became the basis for estimating that the observable universe contains up to 2 trillion galaxies. For many years, the ultra-deep field has been our best map of deep space, a window into the childhood of the universe. Each point of light was not a star, but a galaxy, each containing billions of its own stars. Nevertheless, Hubble's vision, no matter how deeply it penetrated, had its limitations. His mirror, 2 meters and 40 centimeters in diameter, captured mainly visible and ultraviolet light. The oldest galaxies, whose light was stretched due to the expansion of space, sank into the infrared range, inaccessible to Hubble. Between us and those distant celestial bodies lay clouds of cosmic dust, concealing entire populations of galaxies from our view. The ultra-deep field of Hubble, despite all its details, was just a tiny part shaped by the limitations of its technology and the narrow range of the spectrum it could see. It turned out that the universe hid much more than we had assumed, awaiting a new telescope to reveal what lay beneath the dust and beyond the visible. The James Webb Telescope is not just a larger instrument. It is a fundamentally different type of observatory. Its main mirror has a diameter of 6 meters 50 centimeters, which is much larger than Hubble's, and collects more than 6 times more light. But the real breakthrough lies in its capabilities. Webb is tuned to the infrared range, allowing it to penetrate cosmic dust and capture the faint stretched light of the earliest galaxies. Light invisible to Hubble. If Hubble's vision can be compared to peering through a keyhole, Webb's vision is more like stepping back to see a vast mural. For clarity, imagine Hubble's ultra-deep field as a photograph on a single sheet of paper. At that same depth, the mosaic of the Webb Space Telescope would fill a fresco 13 feet high and 13 feet wide. The Webb program utilized the power of the telescope for an unprecedented survey. After more than 250 hours of observations, an area of the sky roughly 3 times the size of the full moon was meticulously studied. Thousands of exposures were combined into a seamless mosaic image, creating the largest and deepest panoramic image of the universe ever assembled. Within this single field, astronomers cataloged nearly 780,000 galaxies, each a city of stars, some shining from less than 400 million years after the Big Bang. This is not just a larger picture. It is a new kind of atlas. The map is deep enough to reveal the weakest and oldest structures of the universe and wide enough to capture the grand architecture of cosmic filaments, clusters, and vast voids. For the first time, astronomers can study not only isolated galaxies, but the entire structure of the cosmos over billions of years, all within a single continuous frame. Webb's infrared vision and wide range of observations opened a new window into the universe, transforming our understanding of its vastness and hidden depths. In the vast mosaic of the cosmos, Webb's nearby universe focuses as a realm of mature galaxies, intricate mergers, and colossal superstructures. Here, astronomers discovered galaxies at the peak of their development, majestic spirals, smooth ellipticals, and irregular shapes caught in the process of collision. The scale of this map allows researchers to trace how these galaxies merge into titanic filaments and clusters, forming the basis of cosmic web. However, among these familiar shapes, one discovery stands out in a special way: a system known as the Galaxy of Infinity. This unusual object, registered at redshift 1.14, has an 8-shaped silhouette. 2 disk galaxies collide almost head-on. Each galaxy remains visible as a compact red core, surrounded by rings of stars and gas, their orbits distorted by the force of the collision. The collision, estimated to have occurred about 50 million years ago, is not just a spectacle of cosmic violence. It created conditions that had not been captured so clearly before. Between two galactic centers lies a vast cloud of ionized hydrogen, glowing with the energy of a hidden engine. Deep observations using the James Webb and Chandra observatories have identified the signature of a supermassive black hole located in the space between galactic cores, embedded in gas, moving at a speed matching the surrounding material to within 50 kilometers per second. This displaced black hole, with a mass of about 1 million solar masses, is accompanied by two others. Each of the original galaxies contains its own active supermassive black hole, confirmed by broad emission lines of hydrogen. The configuration is impressive. 3 hungry black holes, all active, but only one is outside the galactic core, located in the remnants of a collision. Evidence points to a direct origin of the collapse. A black hole formed from dense, shocked gas through merging, rather than being ejected or captured. His presence, captured by the infrared eyes of the James Webb Space Telescope, provides a rare glimpse into how supermassive black holes may arise from the chaos of galaxy formation. The galaxy infinity serves as a testament to the power of the panoramic map.
Только благодаря исследованию такого широкого и глубокого поля астрономы смогли заметить такое мимолетное и сложное событие.
Its figure in the shape of an 8, with a black hole growing in the void between the parts, hints that the most massive engines in the universe can sometimes ignite, not in the hearts of galaxies, but in the turbulent space where worlds collide. Now we delve into the mosaic of the cosmic web, returning to the era that astronomers call the cosmic noon, a time about 10 billion years ago when the universe was least restrained in creating new stars. The galaxies found here are not just energetic, they are organized, showcasing a maturity that defies expectations. The infrared vision of the Webb now reveals a striking contradiction. Galaxies that have ceased star formation, known as fading systems, are abundant here at a time when they should be ablaze with star formation. These sleeping giants, some of which have masses comparable to the largest elliptical galaxies of today, are peacefully settled among a cosmic landscape that, according to theory, should have been filled with young chaotic systems. But the surprises don't end there. The Webb discovered spiral galaxies with clearly defined spiral arms, their disks stable and symmetrical, even with redshifts between 2 and 3. In cosmic scale, this is just a few billion years after the Big Bang. Ordinary models suggested that creating such ordered structures would take much longer, but spiral arms gracefully wrap around dense cores, and some galaxies already show central bars, signs of a mature disk. Data shows that the disks capable of supporting these structures were widespread much earlier than anyone expected. This early order is not just a matter of visual elegance. The presence of stable disks and extinct giants at cosmic noon means that the processes halting star formation and shaping galaxy structures must have acted with astonishing speed. The time frames for the formation of complexity in the universe are compressed. Each galaxy of this era becomes a hint, evidence prompting astronomers to reconsider how quickly and how often the cosmos can shift from chaos to order. The map becomes not only richer, but also rewrites the rules of galaxy formation. At the edge of what the Webb can see, the record for the farthest confirmed galaxy now belongs to Jade's GSZ 14-0. Its light began its journey only 290 million years after the Big Bang. A little behind, MOEMS 14 sets a new benchmark at 280 million years. Both galaxies have been spectroscopically confirmed, their distances recorded thanks to the clear Lyman lines in the near-spec Webb data. But surprises go even deeper. ALMA recorded the emission of oxygen in Jade's GSZ 0, indicating the presence of heavy elements in this early period, confirming that at least one generation of stars has already lived and died. These galaxies shine with the brightness of hundreds of millions of suns, compressed into tiny, intense, star-forming bursts. Their existence and chemical traces indicate that the formation of galaxies and the evolution of stars began at a speed that contradicts standard cosmic chronology. For the first 300 million years, the universe was already actively creating complexity. New findings from a recent survey are prompting astronomers to rethink the history of the universe's formation. It is now known that galaxies and black holes formed earlier and grew faster than models allowed. Even the most distant confirmed galaxies, such as Jade's GSZ 14-0 and MOMZ 14, already shine with heavy elements just 200 to 800 million years after the Big Bang. This means that the cycles of birth, death, and enrichment of stars had to begin almost immediately. compressing what was considered a slow, billion-year process into a rapid cosmic sprint. Standard cosmic chronology, once a slow path from simplicity to complexity, now appears as a rapid sequence of assembly and transformation. The pace of reanimation, the growth of massive galactic shells, and the formation of black holes require new explanations. The first chapters of the universe's history are being rewritten, and the remaining questions will drive research for many years. In just 250 hours, the James Webb Telescope mapped nearly 780,000 galaxies, almost 80 times more than the Hubble's Ultra-Deep Field Survey in 2004. This infrared panorama reveals structures and galaxies dating back 13.5 billion years, including record holders like JADE's GS Z14-0 and MOMZ-14, both observed less than 300 million years after the Big Bang. JWST data shows that mature spirals, massive mergers, and heavy elements appeared much earlier than existing models predicted. However, key questions remain. How did galaxies and black holes grow so quickly? What role did dark matter and feedback processes play? The chronology of cosmic evolution is rewritten with each new observation. However, this overview covers only a small part of the sky, reminding us that our universe is much larger and more complex than we ever imagined, and there is still much to discover.